Hello everybody and welcome to this final section on the notes Octave with Spice, and this is about solving product mix problem with GLPK. So if you look at the notes, so we are here at the page 24 or the page 38, so this is a relatively long section. So this will be split into many videos, but in any case, let's get started. So first, if you recall that we have now modeled a problem, this Muad Deep's bakery problem as an LP, which was basically one way of looking at this. So we have found out a vector C, a matrix A, and a vector B, so that the problem basically says that we want to maximize Z equals C prime C transpose X, subject to the constraint that A times X is less than or equal to B and X is positive. And of course, now since this is a mathematical model for it, we can basically forget where it came from in order to solve it. The Octave will not care, and the mathematical algorithm will not care what are interpretations of this problem. So basically, we are looking a way to solve a problem like this. Maximize Z equals C prime X subject to constraints AX less than or equal to B and sign constraints X is unknown negative. Okay, and how to do this with Octave? So Octave has a GLPK function, GNU Linear Programming Kit, and that's how you that can solve LPs, linear program, what we have here, and also so-called MILPs, mixed integer linear programs. You don't have to worry about what those are. I think in this course we mostly don't have them at all. So let's have a short look here. What would be this GLPK be like? And here it's documentation, and let's have a function index and GLPK. And double click here so it opens, and here is the help for that. Blah 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 blah. So quite a lot. And let's have the same, sorry about that, same here. So what I've simply done here is I printed the help GLPK, and you can see that this is a rather complicated function or versatile. It's not even the help how to use it, it's kind of longish, so 200 and something, more than 300 lines. Do we get 400? Yes, we get 400. 405 lines. Okay, so quite a lot, and obviously there is a lot of stuff here that we don't care about, we don't need to know. So it's in practice it's not that complicated. It's usually relatively simple to use it most of the time. Sometimes there may be complications. So let's try not to understand everything here. Let's just try to figure out how to use this, and this is of course typical for many non-trivial functions, so many things that when you read the instructions, there are lots and lots of stuff, the instructions that you really don't care about. So let's go back to the top here and try to understand a little bit what this is. So help GLPK, as it states there. Okay, so far it's GLPK is a function from, apparently in my system it's there, your system probably somewhere else. Okay, we don't care about that. This is what we care about really. So this minus here, this is as typical in these help files. It somehow gives the syntax of this function, how to use it. So apparently there are a lot of output numbers, xopt, fmin, rnum, extra. Okay, equals GLPK. Okay, then the inputs, there are C, A, B, L, B, U, B, C type, var type, sense, param, quite a lot. So how does this work? Okay, let's try to say, look at. So first there's given 3 arguments. Okay, this is something that we haven't seen yet with Octave, but this is rather typical. So you can have lots of arguments, but not all of them are necessary. So you can only give some of them. And usually if you give only 3 of them, the rest are kind of omitted, and then some kind of default values are used for them. It's also true for that this output, so it can output actually 1, 2, 3, 4 different things for us. And if we ask for 4 things, it will give us 4 things. But we can also ask only, for example, just one. Then in this case is xopt, whatever that is given to us. If we ask 2 xopt and fmin, then 2 of them are given, and so on. But of course, if we want to get this, then we have to ask for all 4 of them, because otherwise it doesn't. These names here are just placeholders. The only thing that matters here is the order. So this is the first output parameter, this is the second output, third output, the fourth output, and this says this is the first input, second input, third input, and so on. The names are there just for, you can change the names for whatever you like, basically. Okay, so let's see. So if I only give 3 arguments, this somehow corresponds to what, maybe this is what we should only do. So C, A, and B here. Okay, they are all capitalized here, which I find extremely annoying, but that's the way they do it. So we had small c, big A, and small b. This was precisely as our problem was described in this 4.5. So C, A, and B defines everything. Maybe we could use this only just giving C, A, and B and forgetting the rest. And it actually now starts to look good. It says somehow that given 3 arguments, GLPK solves the following. Okay, this is called standard LP by GLPK. So minimize, so the C prime times X, so C transpose X, that's basically what we have here, but we want to maximize. GLPK default, it assumes a minimization. That's bad. Maybe not too bad. Maybe we can turn maximization and minimization around somehow easily. And actually we could. But the next is A times X and B. Okay, this is good also. This is what we had, except there's an equality. We don't want equality, we want an upper bound inequality like this. Okay, so 3 parameters is not enough. Oh crap. Well, let's see, we have to read a bit further. But may also solve problems of the form. Okay, so this is the nerdy way of writing minim or max. So this bar like this, or pipe, what this calls is or. Min or max, C prime times X, subject to AX, okay, equals or less than equal or greater than equal B. Okay, this is something that we really want, and X bigger than equal to some, okay, LB apparently means lower bound, and X less than equal to UB, apparently some upper bounds. Okay, so we need to understand a little bit more what is going on here. So basically we want to have not min here but max, and not equal here but this one here. And then X less than equal to UB, this we don't have, but X bigger than equal to LB lower bound, yes we actually do have. the lower bound would be zeros. These are the sign constraints. So we have to look a little bit further. This C, A, B, L, P, U, B, C type, var type, sense param, whatever they are. Let's try to be a bit greedy here and see how fast can we figure out what is the magical spell we have to tell cast to make GLPK work for us. So let's see the input argument C. It's the column array containing objective function coefficients. Okay, that's precisely what we had. A is the matrix containing constraints coefficients. This is what I call a technology matrix. Okay, that's also precisely as we had. B is the column array containing the right hand side values for each constraint in it's like this. Yeah, these are the CAV are the way we want. Next there is an LB. LB is an array. I mean the array is for us array is a vector. Okay. Array containing the lower bounds for each of the variables. Okay, so these we have actually the sign constraints. They have to be bigger than or equal to 0. Funny thing here is actually, if you look at, if LB is not supplied, so if I don't give that at all, then the lower bounds are 0. So this means that the default lower bounds are zeros. Okay, so we don't have to give it. Then UB, this is the array containing upper bounds for its variables. If UB is not supplied, then the default upper bounds are assumed to be infinite, which are, I mean, that's a typical upper bound. If there are no upper bounds, then the upper bounds are infinite, and this is, I mean, almost always our case, since we don't have this that x's have to be like this, or we don't use it. We could use that also. In some cases, it's useful. But usually, I don't care about that kind of modeling. Okay, but we still haven't found out how to make this equality into upper bounds. But this is, now we get it. So C type, so that's the next input variable. So this is an array of characters. Okay, now this is previously one to a matrix in vectors with numerical values. Now this is not, this is an array of characters. So this is the first time we will have a variable that is not numeric. So it's characters containing the sense of each constraint in the constraint matrix. So it has to do with these. So how are they written? And now there are actually f like a free. This means that if we want to ignore a constraint, we can do it. Well, one could ask, why would we ever want to write a constraint and then ignore it? That is, remove it. Well, maybe it's useful sometimes, I don't know. We are not going to use it. If we don't want a constraint, we don't write it. U. This an inequality constraint with upper bound. U like an upper bound, meaning note the colon notation here. So the ith row times the matrix X is less than or equal to bi. So this is what we have. So we have use. That's nice. Okay. Now we know what is the C type there. Next what is the var type? Let's go, do we need this? Var type is a column array containing types of the variables. Actually, it's not a column array, it's a character array. There is a mistake for those who wrote this help text. Sorry about that, not my fault. You can complain to people who wrote the octave. Again, so this is for each variable. So we have 3 variables in our example. We have to say whether it's a continuous variable or integer variable. So this is a subtle point actually technically, but for this course we will choose C. Everything is continuous for us. Continuous things are nice. But what else? Sense. Okay, what is this? If sense is 1, the problem is a minimization. If sense is -1, then the problem is a maximization, and the default is 1. So default is minimization, and we usually maximize. So we have to give that to be 1. All right, this was. I hope you got the idea. If not, of course you can watch the video again. But in any case, we will be doing using GLPK in different settings a lot, so you will get a lot of repetition here. But in any case, let us now somehow go a little bit further. So here is the text in the notes. So this is basically what I said by looking at the help text. So there we have a CAB to start with, then a little bit about other stuff what we put there. Basically upper bounds are use, so 3 variables we assume continuous, so var types is CCC. One thing to note that now these are character arrays, so it means that they have to be put into quotations, either double or single, it doesn't matter, you can choose which one you like. And yeah, the sense was the sense of the optimization, either maximization or minimization. So minimization was the 1, that was the default, and we have to change it to maximization, so sense will be -1. So putting this all together, and without going to solve the system yet, so this is formally how we should call this GLPK. And this is a very typical that we call it this way. So we are actually asking only 2 output variables. We are asking x max, let's call it like this, for example. So this is the optimal solution. Optimal values for x1, x2, and x3 in this more deep case. So optimal number of Atreides, Corino, and Harkonnen cakes that we should make. Then the second one is zmax, so this was called fopt. Okay, we can call it whatever. So this is a z and underscore max. So this is the, just use the max there for the maximization. Of course, I could have used different name, simply z, for example. So this is the value of the objective function and the maximum. And then there were these error numbers and extras. I don't care about them at the moment, so I only ask for these 2 values and separated by comma here. So then I call GLPK, and this is always how it starts, CAB, if it's in the what I call standard form. So I call, sorry about this, but let's scroll back a little bit. So this was the 4.5. If it's an LP and it's this kind, I call it the standard form, when there is an upper bound here and maximization and sign constraints. Unfortunately, what is a standard form? Here in the help, the standard form for GLPK is the equality, and it's actually a minimization. So it's not standard what is standard. In any case, let us try not to be confused about that and concentrate basically on this. This is the kind of, well, in my standard form LPs, the solutions will be always in these lines. So C, A, and B are given here. Then there are, this looks kind of funny, it looks like something is missing. So there is just a bracket open and bracket close. So what is this? This is nothing. Nothing in the sense that this is an empty matrix. Empty matrix is a 0 times 0 matrix. It doesn't contain anything. I have to give it there just to point out that I don't provide here an argument. I just say that use the standard one. Because the first one was the upper bound, and the second one was the lower bound. I don't remember which way they go. went. Let me look at here. Okay, let me use this. Okay, too much info. I have to scroll back. A lot. So here, so first was the lower bounds. So these were the zeros, but that's the default. So I tell Octave to use the default. I could put their matrix vector of zeros also if I liked. And upper bounds I don't have, and that's also the default. So LB and UB, in practice almost always we will use the defaults, which means that we don't pass the arguments, but since the arguments are given in their order, we have to just put there couple of empty things, meaning that use the defaults. Okay, then there was this C type, that was the constraint type. So how many constraints we had? We had 5 of them. So the sign constraints are not here. These are the for the powders, 1, 2, 3, 4, 5 powders, and they were all upper bounds. So this 5 of them. So there are 5 U's for each constraints, each row. U are an upper bound, and I have to put them in the quotations because this is a string of U's. It's otherwise it would be understood as variable names, capital U, capital U, capital U, capital, and so on, and it has to have some value. So this is a literal, not a variable. And I had 3 variables, decision variables, and each of them I assume that they are just continuous. So this is the string again in the quotations of 3 C's. And finally I have to give the sense as a maximization, so this is a -1 instead of +1, which could have been omitted since the minimization +1 is the default, maximization is not, so we have to give this argument. And then there was finally this additional input parameter param, which is for tuning purposes, and at this point we don't care about it. Okay, this was everything for this video lecture. So this was short, believe me, this was as short as I think is possible, introduction how to use the GLPK. And we haven't still solved the problem. We will solve this problem in the next video. See you there. Bye.